The universe's expansion is one of the most significant discoveries in modern cosmology. Here's a detailed explanation of why and how the universe is expanding. The idea that the universe is expanding is closely tied to the Big Bang theory, which posits that the universe began as an incredibly hot, dense point around 13.8 billion years ago. From this initial state, space itself started to expand, causing galaxies to move away from each other. In the 1920s, astronomer Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they seem to be receding. This observation is summarized by Hubble's law, which shows that the velocity at which a galaxy moves away from an observer is directly proportional to its distance from the observer. This relationship indicates that the universe itself is expanding. The expansion of the universe is not like an explosion where matter is flying apart into empty space. Rather, it's space itself that is expanding. Imagine the universe as a balloon with galaxies on the surface. As the balloon inflates, the space between galaxies increases, causing them to move apart from each other. As space expands, the light from distant galaxies becomes stretched, leading to a phenomenon known as the cosmological redshift. The wavelength of the light increases as the universe expands, shifting the light toward the red end of the spectrum. This redshift provides evidence for the universe's expansion. Observations in the late 1990s revealed that the universe's expansion is not just continuing, but accelerating. This discovery led to the introduction of a mysterious force called dark energy. Dark energy makes up about 68% of the total energy in the universe and is believed to be responsible for driving the accelerated expansion of space. While dark energy's exact nature remains unknown, it appears to act like a repulsive force that counteracts the pull of gravity on large scales. The idea of an expanding universe was theoretically predicted even before Hubble's observations by Albert Einstein in his theory of general relativity. Initially, Einstein included a term called the Cosmological Constant, represented by the Greek letter lambda, in his equations to allow for a static universe, as he believed the universe was unchanging. However, after Hubble's discovery, Einstein reportedly called this his biggest blunder, realizing that a dynamic universe was a natural solution to his equations. Today, the cosmological constant is thought to be a possible explanation for dark energy. The expansion of the universe likely went through a phase of inflation shortly after the Big Bang. This inflationary model, proposed by physicist Alan Guth in the 1980s, suggests that the universe underwent a rapid exponential expansion within the first tiny fraction of a second. Inflation explains several observations, such as the uniformity of the cosmic microwave background radiation, the flatness of the universe, and the distribution of galaxies. The role of gravity in the cosmos is quite fascinating. While space itself expands, gravity works on smaller scales to pull matter together. This is why galaxies, stars, and planetary systems remain bound by gravity despite the overall expansion of space. On larger scales, however, the expansion of space overwhelms the pull of gravity, causing galaxies to move apart. Some key observable effects of the universe's expansion include cosmic microwave background radiation, often abbreviated as CMB. This radiation is a relic of the early universe and provides a snapshot of the universe when it was only 380,000 years old. The CMB is remarkably uniform, which is consistent with the idea of an expanding universe. Another effect is the large-scale structure. The distribution of galaxies and clusters in the universe follows a pattern predicted by models of cosmic expansion. These structures reflect the influence of both dark matter and dark energy over billions of years. The continued expansion of the universe raises questions about its ultimate fate. There are several possibilities. One is the Big Freeze. If dark energy continues to dominate, galaxies will move farther apart, stars will eventually burn out, and the universe will slowly cool. Another scenario is the Big Rip. In some models, dark energy could become so dominant that it tears apart galaxies, stars, planets, and eventually even atoms. There's also the Big Crunch. If the expansion slows and reverses, a scenario now considered less likely due to dark energy, the universe could collapse back in on itself, leading to a big crunch. Lastly, we have the Big Bounce. Another possibility is that the universe could undergo a series of expansions and contractions, bouncing between big bangs and big crunches. The universe is expanding due to the initial conditions set by the Big Bang, and this expansion is influenced by forces such as dark energy. The discovery of this expansion has revolutionized our understanding of cosmology and remains a critical area of research in modern physics.